Section 2.4 is entitled Angle Properties in Polygons. So now instead of looking at just angle properties in triangles, we're going to look at angle properties in all polygons. It doesn't matter how many sides they have, but we'll be focusing on convex polygons. So our goal is to determine the properties of angles in polygons and use these properties to solve problems. So let's explore a little bit. A pentagon has 3 right angles and 4 sides of equal length as shown. What is the sum of the measures of the angles in the pentagon? Pause the video and see if you can figure it out. I'm going to try to make this problem simpler by cutting my pentagon into 2 different shapes. I'm going to take a line and I'm going to split it into a triangle and a rectangle. So the sum of my interior angles of my rectangle is 4 times 90 degrees because we have 4 angles and they're all 90 degrees, which gives me 360 degrees. I also know that the sum of my interior angles of a triangle is 180 degrees. Therefore, I know that my total sum of my interior angles of my pentagon is 360 degrees plus 180 degrees, which equals 540 degrees. So now I know the sum of the interior angles of a rectangle, a triangle, and a pentagon. But what about all the other polygons that we can possibly make? Well, we'll get to that. Example 1 states that we need to prove the sum of the measures of the interior angles of any n-sided convex polygon. A convex polygon is a polygon in which the interior angles measure less than 180 degrees. So all of these inside angles are less than 180 degrees. But if we look at a non-convex polygon, we have an interior angle that is much more than 180 degrees. It's more than a line. So to prove this, I started out by drawing my n-sided polygon. To do this, I just put arbitrary number of angles down all the way up till C9, and then I connected C9 to my nth side by using a dotted line, just to indicate that it's almost infinite. It can be as big as you possibly want it to be. And then, after that, I think I'm going to split up my shape into a bunch of triangles, because I know that the sum of my interior angles of a triangle is 180 degrees. So now inside my n-sided convex polygon, I have n number of triangles. So if I'm trying to find the measure of the angles in n triangles, I simply multiply 180 degrees times n. So now I know that the sum of the measures of all of these angles in these n triangles is n times 180 degrees. But at vertex A, each triangle shares this point, and each of these angles at vertex A does not count towards my angles in my polygon. So all of these angles at vertex A, when they're put together, form a circle. And we know that the measure of a circle is 360 degrees. Therefore, the measures of the interior angles of our n-sided convex polygon is 180 degrees times n, our number of sides, minus 360 degrees. And if we factor 180 degrees out of this expression, we get that the sum of the interior angles of a convex polygon with n sides is equal to 180 degrees times the number of sides minus 2. In example 2, we're going to use what we've just learned. Outdoor furniture and structures like gazebos sometimes use a regular hexagon in their building plan. Determine the measure of each interior angle of a regular hexagon. Well, first let's look at what is a regular polygon. So a regular polygon is a polygon that has all angles equal in measure and all sides as the same length. So we know that all of our angles inside of our hexagon are going to be the same measure. So now we know how to find the sum of all the interior angles of a hexagon, so let's do that first. So using our handy-dandy formula for the sum of the measures of interior angles of a polygon, which is S of n is equal to 180 degrees times n minus 2, where n is the number of sides in our polygon. So n in this case is going to be equal to 6, because that's how many sides a hexagon has. So then we have the sum of a 6-sided polygon is equal to 180 degrees times our 6 sides minus 2, which is equal to 180 degrees times 4. So the sum of all the interior angles in a hexagon is equal to 720 degrees. But how do we find just what one of those angles is going to be? Because it's regular, we know that all of our angles are equal in measure. So we have 6 angles that are equal in measure and that add to 720 degrees. Therefore, if we divide 720 degrees into 6 equal parts, that should get us our measure of one angle. Dividing 720 by 6 yields 120 degrees. Therefore, the measure of each interior angle of a regular hexagon is 120 degrees. Now I'd like you to pause the video and try the your turn. Determine the measure of each interior angle of a regular 15-sided polygon called a pentadecagon.
I sketched a regular pentadecagon. Then I wrote the expression for the sum of the measures of all the interior angles of any convex polygon. A pentadecagon is a convex polygon that has 15 sides, so n equals 15. The sum of the measures of the interior angles is 2,340 degrees. A regular pentadecagon has 15 interior angles, and all of these angles are equal, so I divided the total by 15. The measure of each interior angle of a regular pentadecagon is 156 degrees. This looks reasonable based on my sketch, since the interior angles are much greater than 90 degrees, but only a little smaller than 180 degrees.
Example 3 has us visualizing tessellations. So for those of you who don't remember, a tessellation is a pattern made of identical shapes. The shapes have to fit together without any gaps, and they also should not overlap. So a floor tiler designs custom floors using tiles in the shape of regular polygons. Can the tiler use congruent regular octagons and congruent squares to tile a floor if they have the same side length? So first, let's find the measures of the interior angles of our shapes. So to find the measure of the interior angle of a square, well, we already know that one angle inside of a square is 90 degrees. So let's find the sum of the interior angles of an octagon, and then from there find what one interior angle of a regular octagon is going to be. So we have that S of n is equal to 180 degrees times n minus 2, and the number of sides in an octagon is 8, so my n is going to be equal to 8. So we have that S of 8 is equal to 180 degrees times 8 minus 2. S of 8 is equal to 180 degrees times 6, which is equal to 1080 degrees, and that's the sum of all the interior angles of our regular octagon. But we know that each angle in our regular octagon is going to be equal. So if we divide 1080 degrees into 8 equal parts, we'll get that each interior angle in an octagon is 135 degrees. From here, we need to do a little visualizing. So we have two octagons that fit together, and they form an angle that measures 1 times 135, 2 times 135. So they form an angle that measures 270 degrees. So next we need to find what this gap is that we need to fill in order to make this a full circle. So if you remember, the measure of a circle is 360 degrees, and we have two octagons fitting together making an angle of 270 degrees. So if we find the difference between these, we get that 360 degrees minus 270 degrees is equal to 90 degrees. We know that the interior angles of a square are 90 degrees. So because our side lengths are the same, our square fits in here just perfectly. So once we have our 360 degrees filled in, this can simply repeat over and over and over and over again, forming a tessellation. Now I'd like you to try the your turn. So can a tiling pattern, or tessellation, be created using regular hexagons? Hexagons have 6 sides, remember, and equilateral triangles that have the same side length. And then explain your answer. So I want you to pause the video and just see if you can visualize or try to make this tessellation.
I needed to find out if I could create a tiling pattern using regular hexagons and equilateral triangles that have the same side length. I started by determining the sum of the measures of the interior angles of a regular hexagon. It is 720 degrees. Then I divided by 6 to determine the measure of each interior angle in a regular hexagon. The measure of each angle is 120 degrees. The measure of each interior angle of an equilateral triangle is 60 degrees. For a tiling pattern, the shapes must form a 360-degree angle without any gaps at the point where they meet. 2 regular hexagons and 2 equilateral triangles do form a 360-degree angle without any gaps at the point where they meet. 1 regular hexagon and 4 equilateral triangles also form a 360-degree angle without any gaps at the point where they meet. Therefore, a tiling pattern can be created using regular hexagons and equilateral triangles that have the same side length.
So what we've learned in this section is that you can prove properties of angles in n-sided polygons using other angle properties that you've already proved. The new things we learned is that the sum of the measures of the interior angles of a convex polygon with n sides can be expressed as 180 degrees times the number of sides minus 2. The measure of each individual interior angle of a regular polygon is 180 degrees times the number of sides minus 2, all divided by the number of sides. The sum of the measures of the exterior angles of any convex polygon is 360 degrees. I want you to try and prove this last one, and then we'll discuss it in class.